Okay, so recapping from what we did last time, we had a quick introduction on the frequency domain representation. As a reminder for that introduction, I just want to remind you that we mentioned something like this. Any signal, right, is in fact a function of both time and frequency. And this is your signal. So let's say X. It's generally speaking a function of both time and frequency. And of course there is a relation because it's the same signal. It just depends what you want to look at in terms of observing the signal. I gave you the example for that last time. I said if you are listening to a piece of music or a symphony played by a band, then there are two ways to look at that. One person would be sitting there observing how loud the overall music goes with respect to time. So the volume goes up and down as time passes. That's a person who's looking at the signal as a function of time. Okay, so that's x of t. And another person from the audience is sitting there and he or she is actually more interested in which note is being played right now by a particular musician or which instrument is being played over the time. So across all time, how much this instrument has been played and with what volume. So that's a person who's looking at the signal, right, in terms of amplitude or power as a function of frequency. There is a relation between both. And if you look only at the time domain, so you are facing the x versus t, the other one becomes completely orthogonal to you, so you don't see it. You don't see that information. You are caring collectively about the volume versus time. If you are looking from this side, so looking into the signal versus frequency completely, or if you rotate the axes so that you see only x versus f, then you will see the amplitudes versus different frequencies. So how much volume you had for each note, but you forget completely or you cannot see completely what happened versus time. Okay, that's what we are looking at in this course. So either you look at as a function of time or you look at the signal as a function of frequency. But in fact, in more advanced signal processing approaches, you can actually rotate the axes such that you see both. So similar to the figure that we see right now, you can see both at the same time, and that's called the time frequency analysis of a signal. So you are looking at the signal as a function of time as well as a function of frequency. Most of the higher end applications like radar processing, voice recognition, and all these applications, they use that dual view. So they see both of them at the same time. They don't look at one completely or the other completely, but they rotate the axes or they look at the view as a three-dimensional view. So you have volume versus time and frequency at the same time. But we are not addressing this as part of this course. So that thing we discussed last time. And then as part of preparing you to understand where actually the Fourier transform came from, we had a quick discussion about the concept of orthogonality in vectors. So when you multiply the dot product of two vectors, if they are orthogonal to each other, the dot product of those two vectors is equal to 0. If they are not, then the dot product is a way to measure how much one of them can be represented in terms of the other, or what we call the projection. And then we said a very similar concept exists for signals or functions of time. So we are no longer here looking at vectors, but we are looking at a function of time x of t, right? And then I have two functions, x of t and y of t, and I want to see whether those functions are orthogonal to each other or not. The measure that we used to do that was discussed last time and was called the cross correlation between the two functions. So you multiply the two functions together and then you integrate the result of the multiplication over the whole time duration. If the result of this integration is equal to 0, this means, or we call those two functions orthogonal functions, which means that you cannot really represent one of them in terms of the other. They are completely like perpendicular to each other. If you try to represent one of them in terms of the other, the result of that representation is going to be 0, okay, because they are orthogonal functions. And this particular concept is quite important, we will see later on, to understand how the Fourier transform is performed. How do you represent a signal which is given to you in time domain in terms of its frequency domain representation, and how you get it back to look at it in time domain. Before going into that, we just remember that this guy, as a bit of history, so Jean-Baptiste Fourier is the guy who actually came up with, he's a mathematician, a French mathematician, and he's the guy who came up with the whole concept of looking at things from a frequency and time domain perspective. At this part of the course, when we look at the time domain signals and how they are represented as frequency domain functions, we are looking only at this part, this chapter, we are looking only at periodic signals. They are easier to understand. Their analysis in the frequency domain is a little bit easier, so that's why we start with the periodic signals. And the representation of a signal in frequency domain is basically done by analyzing that signal into individual sinusoidal functions, right? So why? Because each sinusoidal function, as a function of time, represents a single frequency existence, right? The meaning of the word frequency comes actually from sinusoidal functions, okay? So when we say that we are representing a signal in the frequency domain, we are basically breaking down that signal into multiple components. Each one of them is a single sinusoid, okay? Now, single sinusoid, a sine or a cosine, or in general, a complex exponential, e to the j omega t. Because as we discussed earlier, e to the j omega t is simply a sine and a cosine combined together using the complex representation, and each one of them has the exact same frequency, right? It's a sine omega and a cosine omega combined together. So we agreed that e to the j omega t by itself is a single frequency signal, even though it has two components, a sine and a cosine, but both of them at the same frequency. So it's a single frequency component. So in general, when we say we are trying mathematically to represent a signal in frequency domain, we are trying to break down that signal into different e to the j omega. For each one of them, there's a different frequency. So we are trying to represent our signal x of t, right? Okay, as a summation of few e to the j omega n t. And we sum over n, right? And then these components, each one of them has a single frequency, are probably multiplied by some amplitude. I don't know what's the value of that amplitude, right? We don't know. Each one of them has a single frequency and can be with a certain amplitude. If you combine those together, and they were actually coming from the original signal, this combination should add up to the value of the signal x of t, okay? So again, x of t is a time domain signal, it's a function of time. In order to break it down or to look at it from a frequency perspective, still we try to present that as a combination of e to the j omega nt. Why e to the j omega nt specifically? Because this is the signal that represents a single frequency. So I can eventually say that when I look at this signal from the frequency domain perspective, I really don't need this, I just need the d. Because as soon as I know what's d1, what's d2, what's d3, and so on, right? I know exactly how much of that signal at frequency omega 1, how much at frequency omega 2, how much at frequency omega 3, and so on, okay? And accordingly, I know how it looks like in terms of amplitude versus frequency. So when I am plotting the signal in frequency domain as a function of f, or in general omega, the radiant frequency, again, the relation between them is just omega is equal to 2 pi f. It's just a scaling factor of 2 pi, okay? So if I represent my signal as a function of omega, the general representation is going to be those guys, d1, right, d2, and their corresponding frequency, omega 1, omega 2, and so on, both in the positive and negative direction. So I can have, mathematically, I can have both the positive and the negative frequency components for my signal, okay? So again, this is a time domain signal, which looks like a function of time. If I want to look at it in a frequency domain, as soon as I can manage to represent it this way, then those dn, d1, d2, and so on, when plotted versus frequency, will give me the representation of the signal in frequency domain. Now this case where you have those D1, D2 at omega 1, omega 2, so discrete representation, this happens when x of t is periodic. Okay? So if x of t is not periodic, this representation is not valid. And we will address this situation where x of t is aperiodic in the next part of the course, inshallah. Okay? But for now, we start with the periodic case. For the periodic case, it was this guy, Fourier, who said that you can, and he has some mathematical representation or proof for that, you can represent your signal as a summation of, if it's periodic, you can represent it as a summation of individual frequency components, discrete frequency components. Each one of them happens at a particular frequency, and we will see which frequencies exactly. We will see that in a minute, okay? And each one of those components has a certain amplitude factor or a certain coefficient, right? That coefficient versus the different frequencies that it exists at is how we look at a signal from a frequency domain perspective, okay? Any questions so far up to this point? Now, why actually this representation, right, was useful and important in terms of analyzing signals and systems? So in terms of function representation, it might have its other like physical meaning, looking at frequency domain and so on. But why do we really care about looking at frequency domain? This is also what we tried to touch upon last time when we mentioned that the nice thing is if I can represent my signal x of t as a summation of some complex exponentials, right? Then imagine that this is the situation. I have a system, right? And I have the input to this system, x of t, right? And I have the h for this system. And then I have the output, y of t. We learned earlier that if you look at things as function of time, and that's it, then your only option to calculate y of t is to perform the painful convolution between x of t and h of t. Yes, convolution is painful. It's a very expensive operation, right? Okay, but that was our only option. We are talking here about linear and time invariant system. If the system is not linear and time invariant, it becomes even a more complicated situation, okay? So for a linear time invariant system, if I know the input and I know the impulse response, my only way to calculate the output is basically to perform the convolution operation, which includes shifting, inversing, and multiplying, as well as integrating. So it includes all these operations while performing the calculation of the convolution. And even if you do that on a computer and you are dealing really with like world scale signals, so actual signals that extends over a large time duration, still the convolution operation is a very expensive operation and can take a very long time to calculate. Okay, so well, imagine that if we break this signal into this format. So it becomes x of t is equal to a summation of some constants, the dn's, right, multiplied by e to the j omega nt. Okay, so what happens? Due to a particular property of linear time invariant system, and that property says that the exponential function is an eigenfunction of any linear time invariant system. What does an eigenfunction means? It means that if I have a linear time invariant system and I put at the input any general exponential function, e to the power st, I get at the output the same exponential function exactly multiplied by some factor, which is a constant with respect to time. It's no longer that factor multiplied by the exponential is a constant. So imagine if I break my input signal, x of t, into a bunch of complex exponentials, what will I get at the output? The same thing that I put into the input, so the dn and the e to the j omega n. So for each one of those e to the j omega 1, omega 2, omega 3, and so on, I will get it exactly the same at the output, and then multiply it by this constant thing, right? So I know that the output is going to be represented again by a summation of a bunch of exponentials, which are exactly the same as the ones that I put to the input, but the difference is that those exponentials are scaled now with some factor, and I need to calculate this factor. We found by doing, and it's in the next slide, that factor is equal to the integral from minus infinity to infinity, the impulse response of the system multiplied by the function e to the j minus j omega nt dt. So if you can solve this integral, if you can find a solution for this integral, which is, by the way, mathematically, generally speaking, integration of something multiplied by exponential is much easier to solve as opposed to something like solving the convolution for general functions, okay? Anyways, so if you can solve this, which is going to be this constant, then you know the constant, and you know that the output is going to be the input multiplied by those constants added together. Because of the linearity of the system, a single exponential produces itself multiplied by a constant. A summation of those exponentials will be produced, because of the linearity, will be produced the same, each one multiplied by its own corresponding constant, right? And that constant can be calculated. We don't care about calculating that constant now, but you just need to know that it can be calculated from that equation. Later on, we'll come to that, okay? So, nice, because now I can figure out the output, knowing the input by doing this analysis, and I no longer have to do any convolution to calculate the output from the input, right? Okay, so I can now calculate the output from the input using this property and this representation, okay? And the only extra thing that I need to calculate is this constant, which is called the Fourier transform of the system, the transfer function of the system, okay? That's the whole story in terms of, first of all, what does the Fourier analysis represents? It breaks down the signal into its own individual frequency components, and the coefficients of those frequency components are what we call the spectrum of the signal, or the frequency domain representation of the signal, okay? And why this is useful in the systems theory, because because there is this property that an exponential input to a linear time invariant system produces itself again, the same exponential exactly, but with some constant multiplied with it. Then, if in general I can break the signal into a bunch of exponentials, which is what we call the Fourier series representation, then I can calculate the output using the same exponentials and the constant without really having to do any convolution in the process, okay? This shows, again, this eigen property with some derivation for it, and the usefulness that I mentioned a minute ago, that you can represent your input in terms of its Fourier series, and then you get the output calculated. Now we go to this situation, okay, which says that, okay, now if I give you the dn's for a particular system, so this first equation, which we have already seen before, right? If I give you, I tell you that the signal x, right, when you look at it from a frequency domain perspective, and let's call that x omega n, for example, okay, that signal looks like those d's. So some d1, d2, d3, and so on. Maybe an infinite number of those. So I have the dn, okay? And I ask you, what is the time domain representation of that signal? It's very easy. Of course, I will give you those d's and the corresponding frequencies that they occur at. When I ask you what's the time domain representation, you will simply tell me that x of t as a time, as a function of time, is equal to the summation from n equals minus infinity to infinity, those d's multiplied by their corresponding, okay, let me write it as we wrote it before and then explain why, omega n t, right? So simply each one of those factors, each one of those coefficient, each one of those spectral element is multiplied by its corresponding frequency component, which is a complex exponential at that omega, at the omega where the d exists, right? Now the question is, I told you that we'll come to that later, what are these set of omegas? Which omegas exactly that these occur at? The theorem from Fourier analysis says that if x of t, don't forget that x of t is periodic, right? And it has a certain period t, right? And from that period, I can deduce a fundamental frequency, right? Which is equal to 2 pi over t. That is called omega naught, your fundamental frequency of the signal, okay? Now, those frequencies omega n are integer multiples of the fundamental frequency. So if I know that x of t has a period t, I can reduce the fundamental frequency from that, the fundamental period. I can reduce from that the fundamental frequency, which is 2 pi over t, right? And I call that omega naught, and then replace this omega n by n multiplied by omega naught. So when n is equal to 1, you are at frequency omega naught. When n is equal to 2, that's omega 2, you are at frequency 2 omega naught. Omega 3 is 3 omega naught, and so on. When n is equal to 0, you are at what frequency?
DC.
DC. That's 0 frequency. So when n is equal to 0, you are looking at the DC component of the signal. Okay? Okay, so now we know if I have the frequency domain representation, which is the Dn, right? If I have this, and I know the locations of those, so I have that spectral representation, how do I get the time domain representation of the signal, right? So if you give me this, I can plug it into this equation and immediately find an expression for x of t. The question is, how can I find those guys? Dn, d1, d2, and so on, for a given x of t. So now we are trying to solve, so this case is when you have the frequency domain representation, which is the dn's, right? And you want to figure out what's the time domain representation, so you want to figure out x of t. Okay? The question is, what if you are given x of t? How can you find the dn from that? What operation you should perform on that x of t to find the dn, right? And this part shows also kind of the smartness of Fourier. So it was observed, remember we discussed earlier the concept of orthogonal signals, right? And by default, if you perform this operation, if you try to multiply e to the j omega n t by e to the j omega m t, so some omega and some omega that are multiples of the same fundamental frequency, but they are, m and n, okay? But they are different. So n is not equal to m, okay? If you multiply those two signals and you integrate from minus infinity to infinity, or you integrate over one period, because that's the same for this case, right? The result of that integration, so let me do it over one period, because from minus infinity to infinity, you'll find that this is not a solvable integration. So if you integrate over one period, you will find that the result of this integration is always equal to 0. And the only case where it's not equal to 0, when the same omegas exist in both of them. So n is equal to m. So for any situation where n is not equal to m, so you are using two different multiples of the same fundamental frequency, so two different harmonics of the same fundamental frequency, the result of the convolution, the result of the integration is going to be 0. What does this integration represent when we multiply two signals and integrate? This is what we call the cross correlation between the two signals, and this is what checks the orthogonality of the two signals. So now we see that those e to the j omega n and e to the j omega m t, right? They are orthogonal except for the case that they have, it's the same signal, same omega. But for different omegas, they are orthogonal. And by the way, this is the case for your cosine function. So imagine, for example, you have cosine 3t and cosine 6t. If you multiply those two signals together and integrate, and you can try that on your calculator or by hand, by actual integration, the result of the integration is going to be 0, right? The only case is when you multiply cosine 3t with cosine 3t, because in that case you have cosine square, and a cosine square function is broken into a cosine double the frequency and a DC component, a constant component, right? The cosine double the frequency when you integrate it over one period gives you 0, but that DC component gives you some value, right? So the same here, and the only situation where they will give you a non-zero result is when the two signals are at the same frequency, okay? Now, remember, if we go back to the definition of the calculation of cross correlation, we said x of t, right, multiplied by y conjugate of t, right? And I told you that this conjugation, we only care about it when we are dealing with complex signals. The e to the j omega t signal is a complex signal. So in this case, when we are doing this cross correlation, don't forget that we have to do this. So it's e to the j omega n t multiplied by e to the minus j omega m t, right? Okay. Okay, so what happens when they are equal to each other, the same frequency? The result of that integration is gonna give you a value, and that value is exactly equal to the period of the signal. So it's equal to capital T, okay? And if we say that instead of doing this, we do this, so we just divide by T, right? Then the result of this integration is gonna give you 1. In the case, M is equal to N, okay? So in the case M is equal to N, this integration is gonna give you 1, okay? When you divide it by T. Now imagine that I go to x of t, right? And I perform this operation on it. So let's see now how Fourier came up with this, how you can calculate those frequency domain components. So I have x of t, and I decided that I'm going to multiply this by e to the minus j omega n t and integrate with respect to time over one period. Okay, and then divide the result by 1 over t. That's exactly the operation that we talked about here. But instead of, we were talking about one exponential multiplied by the other, now the whole x of t is multiplied by a particular exponential at frequency omega n. What's going to happen? Remember that x of t is a summation of dn multiplied by e to the j omega n t, right? We said that x of t can be represented as a summation of a bunch of complex exponentials at multiple of the fundamental frequency, right? We already agreed that this representation is possible. So replace x of t with this. What will you get? And let's just to make sure that we are not call this omega m, okay? So you end up with the integral over one period, 1 over t, and then you have the summation of dn multiplied by e to the j omega n t, and then the whole thing is multiplied by e to the minus j omega m t. And you integrate with respect to time, right? Now, if m is not equal to n, what happens? 0. So out of all these elements inside the summation, which one that will result in something when multiplied by this and integrated? The only m, right? When omega n is equal to omega m, which means that n is equal to m, right? So for that particular one, when m is equal to n, you have a value, and the value is equal to, of the integral, is equal to 1 after dividing by t, right? So what remains? The coefficient, right? So if I perform this operation, x of t multiplied by e to the minus j, let's say, for example, let's take it with numbers. So x of t multiplied by e to the minus j omega 3, for example, t dt, right? And I integrate and divide by the period. What should I get? The only component of x of t, which is represented by this, right? Omega 1, omega 2, omega 3, and so on. The only component that will give me a non-zero is the component at omega 3. And what's the coefficient of that component? D3, right? And D3 is going to be multiplied by what? 1 over t, the integral of e to the j omega 3 multiplied by e to the j omega 3 with minus, which is going to give me a 1. So the result here is going to be D3. What if I want to get D1? Then just replace this by e to the minus j omega 1t. Then I will get D1. What if I want to get D0? Replace this with 1. E to the power 0, right? E to the minus j power 0. When you replace this with 1, what do you get? Just the integral of the signal over one period divided by the period, which is the average, which is the DC component. So this will give me D0. What if I want D10? Then simply multiply here by e to the j omega 10, and so on. So in general, if I want to get the coefficient dn, it's equal to 1 over t, the integral over one period, the signal multiplied by e to the minus j omega n t dt, right? So now I got an expression how I can calculate the different frequency coefficients from the time domain representation of the signal, right? If I have x of t, I take x of t multiplied by e to the minus j omega n, okay, and I integrate that with respect to time. The result of that integral is going to be coefficient number n from the series or from the frequency domain representation, and that's exactly what we see here when we are performing conversion from time domain representation of the signal into the frequency domain, which is basically calculating those coefficients, the dn, okay? So now we have seen both operations. If I have the dn, which is kind of the frequency domain representation, I have those coefficients versus frequency, right? And I want to figure out how x of t, how x looks like as a function of time, I perform this operation. I just multiply each coefficient with the corresponding exponential at that frequency and sum the result to get the function of time. If I have the function as a function of time and I want to look at it from a frequency domain representation, I multiply the function by e to the minus j omega n. Omega n is simply n omega naught, right? Okay? And I integrate with respect to time over one period, and I divide this by the period. This should give me the coefficients d1, d2, d3, and so on at the different values depending on which n I select. Okay? And if I keep it as a general function of n and I can get it as an expression, then I got a full expression for dn, how they look like as a function of different frequency multiples. Okay? Don't forget that d1 is at omega naught, d2 is at 2 omega naught, d3 is at 3 omega naught, and so on. Yes?
Doctor, the previous integration we did in omega n, and here is the n omega naught.
It's the same. هي omega n.
So we're going to say يعني 2 omega 0 will equal d2.
Yes. So 2 omega 0 is the location of d2. 3 omega 0 is the location of the location, not the value. The value is what you get from the integral. But this value, as a function of frequency, occurs at which frequency? It occurs at d3 occurs at 3 omega naught. d4 occurs at 4 omega naught, and so on. So if you want to plot the signal in frequency domain, let's use the upper part. So if you want to plot your signal as a function of omega, right? It will occur always at, you will have some values at omega naught, 2 omega naught, 3 omega naught, and so on. And also minus omega naught, minus 2 omega naught, minus 3 omega naught, and so on, right? And the coefficients, the corresponding coefficients is going to be this one, is going to be the value, is going to be d1. This value is going to be d2. This value, whatever it is going to be d3, and so on. And in the negative, this is d minus 1, d minus 2, d minus 3, and so on, right? And at the 0 location, you have the dc or d0. Okay? So that's how your signal will look like when you try to plot it. That's a periodic signal. When you do the transformation of that signal into frequency domain, which is calculating those dn's using this expression. From the time domain, you can calculate those, and then you know that their locations occurs at omega naught, 2 omega naught, 3 omega naught, and so on. Okay? One important notice. In general, the d's, those coefficients, are complex numbers. They are not actually real numbers. Okay? So when we plot them, you have to plot the magnitude in one plot and the phase in another plot. Okay? So it's typically, when you see this, it's typically the magnitude plot. So it's not just D, it's the magnitude of D. Okay? And you can have another plot that shows you the phase of D. Most of the time, in good system designs and signal designs, we try to work with situations where the phase has some linear representation. And in that case, we only care about the magnitude of the signal. But in the case that the phase has a lot of variation, keep in mind that the most effective part that really scrambles the signal and makes it look bad as compared to its original representation is if someone plays with the phase of the frequency domain representation of that signal. So if that signal goes through a system and that system does not deal with the phase in a linear fashion, so it scrambles the phase, it applies some non-linear operation on the phase of the different components, D1, D2, the output from that system is going to look quite different from the input. However, if the system plays a little bit only with the magnitude, it doesn't affect the output that much. The magnitudes of the different frequency components, right? But why do we care about the magnitude most of the time? Because we try to design our systems to be linear, which means that, again, playing with the phase means in time domain that you are shifting the signal up or down in time. That's how you play with it. That's what happens when you play with its phase in frequency domain representation. Why does this matter? Remember that those components, right, are components of sinusoids. So you have one sinusoid at 3 omega naught with an amplitude equal to D3. You have another sinusoid which is slower at 2 omega naught with a magnitude D2, right? Now, if you add two sinusoids together, but they are in phase, and you like increase the amplitude of one of them a little bit or decrease it a little bit, but you didn't shift them with respect to each other, the output is not going to change that much. It's going to look more or less the same, okay? But if you don't play with the amplitude, but you just slightly shift one of them compared to the other, the output is going to look quite different from the case where they are aligned together. So that's why we really care about not playing that much with the phase of a signal. That's just a side note, okay, from a practical perspective. Okay, so going back to where we are, now we have those nice representations of signal in time domain. How can I get its representation in frequency domain and vice versa? Basically those two important equations. If I know the frequency domain representation, the dn as a function of different frequencies, n omega naught, I can calculate the time domain, and in this case, I'm moving from frequency domain to time domain representation in this equation. Okay? I have the frequency domain, I'm calculating the time domain. In the other equation, I have the time domain, and I want to represent the signal in frequency domain, so I do this operation. Okay? So that's moving from time to frequency to look at how a signal looks like in frequency domain. Any questions up to this point? All clear? Okay. Another important thing to keep in mind, again, this is just the part that has to do, you are not required to do proofs. Now, I have the proof here just because it makes sense where, or it enables you to figure out where the equation came from, but you are not really, so just not required, okay? You can look at it just for information and to understand what I said, but you are not required to prove the Fourier transform, the Fourier representation, where it came from. You just need to be able to do it and understand what does it mean when I look at frequency domain and what does it mean when I look at time domain. Now, in terms of notation, you have your signal in time domain x of t. You have the frequency domain representation of, we are talking about periodic signals here, the frequency domain representation, which is the Fourier series coefficients, dn, or we call them the spectral coefficients, dn, okay? And you move from one to the other, from x of t to dn, using the integration representation that we saw in the previous slide. And you move from dn to x of t using the summation representation that we saw in the previous slide. dn is called the Fourier series coefficients, or we call it, in general, representation of a signal in frequency domain is called the spectrum of the signal, okay? So we call those the spectral coefficients, okay? If we are dealing with D0 out of those dn's, then we are dealing with the DC component, the component of the signal, or the amount of the signal in terms of amplitude or power that is contained in no frequency variation. So it's kind of a constant amplitude value. That's the DC, or the average value of the signal. We also have the first harmonic, or the fundamental component, the one that occurs at n equals 1 plus or minus. Why do we have a plus or minus? Okay. Again, remember that if you want to represent a cosine function in terms of complex exponential, how do you represent that? So cosine omega t is equal to what? Half e to the j omega t plus e to the minus j omega t, right? This is a relation that comes from Euler's formula. Euler's formula says that e to the j omega t is equal to cosine omega t plus j sine, right? And then if you write the e to the j omega and the e to the minus j omega, you will have a minus sign here. If you add those together, you cancel the sine part and you stay with the cosine, and you have added both this and that. You just need to divide it by half to get the cosine function, right? Anyways, and remember that for a real signal, for a signal in time domain that looks real, it doesn't really contain complex components. A real signal will contain actually either cosines or sines. It's not going to contain an e to the j, right? Okay. So for a real signal, if you have a component at e to the j omega t in frequency domain, you have also to have a component at e to the minus j omega t with exactly the same amplitude, such that when you add them together, they will give you the cosine function. Or when you subtract them, so one positive and one negative, you get a sine function, depending on whether it's a cosine or a sine, okay? So that's why we say that the first frequency component occurs at plus and minus 1, both of them. That's the first frequency, the fundamental component, right? The second harmonic, which is at n equals 2, occurs at plus 2 and minus 2 combined together. Third harmonic occurs at plus 3, minus 3, and so on. So the nth harmonic occurs at plus n and minus n as dual components, okay? In the case of real signal, as I mentioned, right, the plus and minus, and this is shown actually here, the consequence of this is shown in this slide. Again, you don't really need to do any derivations like this, but they just allow you to understand that even though we have the general representation of a signal, right, in terms of its Fourier series representation with this general representation, right? So we know that x of t, generally speaking, can be represented in this formula. X of t is equal to this, right? However, if x of t is real, I can actually represent x of t only in terms of cosine and sine functions without resolving to complex exponentials. And if you do the derivations, you don't need to. You will find that x of t can be written in this form as a summation of cosines and sines at every frequency component with different two real amplitudes, as well as the DC component. Or in another, this is called the trigonometric representation. You can only do this in the case x of t is real. If x of t is not real, then you cannot represent it in this form, and your only option is to represent it this way, okay? If it is real, you can write it this way, or even this way, which is instead of saying a cosine and a sine and the same frequency with different amplitudes, you can combine those into a cosine with another amplitude and a phase shift. Right? That can be done from trigonometric relations. You can make this look compact by doing this. And don't forget that when you do this as cosine and sine, now the summation becomes from 1 to infinity. There is no negative side to it. The only case where we will have the negative is when we use the complex exponentials. Why? Because in that case, the combination of the positive and negative together gives you the cosine function. So that's the meaning of that negative frequency. It just means that this is a real signal which is represented by an actual cosine, and that requires two exponentials at the positive and negative side. Okay? Anyways. So the summary is put here. There are three ways to represent a signal in terms of its frequency, a periodic signal, in terms of its frequency domain representation. The exponential, which is the more general, and that's the one that I want you really to focus on while solving problems and other aspects, because again, once you get this expressed for a particular signal, you can play with Euler's formula and exclude, deduce the others. So it's not really needed to do the others in terms of the calculation. However, you need to know that they exist, which is the trigonometric, either the compact trigonometric or the full trigonometric representation. Don't forget, those two are possible only for real signals. Okay? While this one is general for any signal, whether it's real or not. Okay? And I want you actually to focus on this. Okay? I don't want you to spend a lot of time trying to do the trigonometric analysis. For the trigonometric, there are slightly different formulas to calculate the AN, right? and Bn as well as the A naught. Okay. But again, what I want you to really focus on is this one. Okay, so stay focused on the complex exponential representation of the Fourier expansion. I'm going to stop at this point. I think this is too much to absorb beyond this point, so I'll stop here. We just talked about how we represent a signal, a periodic signal, in frequency domain by doing the Fourier series analysis. We saw how, if I have the time domain signal, I can deduce the different components of the signal in frequency, which will look like a discrete function of frequency, right? And if I have those discrete coefficients or spectral coefficients, which is the frequency domain representation, how I can calculate the original signal from that back to its time domain representation. And we discussed a little bit what's the value of this frequency domain analysis, because it allows actually easier analysis of linear time invariant system and how they interact with signals at the input and the output. That's it. Next time we will solve some problems on this topic so that you get more understanding. And also we'll discuss some of the properties of the Fourier series representation, as well as one important aspect, which is the equivalence of calculating the power of a signal from its time domain representation, which you have been doing already in the previous parts, and how you can actually calculate it only from, if you have the DM, and you want to calculate the total power contained in the signal, how can you do that without having to resort back to its time domain representation? So calculating the power of a signal from the frequency domain representation. These are the two topics that we'll discuss next time: solving problems and the power calculation for different signals.